The name of this video is Infinite Wire with current revisited. In this video, we are going to find out what is the magnetostatic field B of an infinite straight line which carries a steady current I. However, instead of using, for example, Ampere's law and the symmetry arguments as we've done in FIS 242, we are going to use the concept of same equations have same solutions using the mapping we introduced in the previous video. Again, this is a simple problem. The reason why I do it is because it's pedagogical, and I hope it will help you realize the fundamental importance of same equations have same solutions, which eventually you can extrapolate as a concept and use it in different contexts in physics later on in your career. So let us consider, in general, a quasi-filiform, so with some cross-sectional area A, infinite straight wire. And I will tell you in a minute why I want to start with a quasi-filiform wire instead of directly with a filiform wire. Eventually, we are going to go in the limit of a filiform wire. So the top cross-sectional area here in 3D looks like this. This is the wire itself. This is the bottom cross-sectional area. We consider, as always, a cylindrical coordinate system where z-axis coinciding with the longitudinal axis of the wire itself, so this is z. We assume that along z there is a steady current, steady I, which goes in this direction, of course only within the conductor itself. Outside there is vacuum, so there is not DC current, steady current there. The radius of this area is capital R, so the area is pi r squared. Eventually, in the limit at the end, we will go in the limit to 0 plus, so that we recover the purely filiform wire we consider in FIS 242. And of course, we have, this is a cylindrical coordinate system, so there will be an R. And of course, we can also sketch here an X and Y coordinate system if you want, to ease the understanding a little bit. So this is X, this is the origin, and this one is Y, so that a generic point capital P, let's say on the XY plane, will be somewhere here, will be characterized by these components, X and Y. This is my point capital P, so it's either X and Y or R, okay? Of course, here we need to go parallel to this. Okay, that's my Y component. Let me erase this, which is unnecessary. Great. So either X and Y or R for my point P in this region of space here. All right. So now that we know that, we have a steady current. What is, by definition, our steady current? We want to find the vector J. So the vector J is going to have the following components. In general, 3 components. So there will be a Jx component, which in this case is equal to 0, because we point only in the z direction with the current I. Similarly, a Y component is equal to 0, and the z component within the wire itself, well, we know that, what do we know? We know that I is a steady current, which means I has to be equal to the flux of J along the z direction. So it has to be pi capital R squared times J in the z direction, because it's steady current, the flux of J through pi R squared is I, the current density, the current intensity, which is a scalar. So Jz is I over pi R squared. So in this one is for each point R in the region from 0 to capital R included, which is within the wire. Of course, outside the wire, J will also have 3 components, but they will be all equal to 0. So this is outside the wire. I'm not going to write, well, let's write actually for generality down here. This is for R in capital R excluded, because here is included already here. So in vacuum is excluded all the way to plus infinite. Eventually, when we will go in the limit for R that goes to 0 plus, we are going to effectively extend this R all the way to 0, and then we recover the case of a filiform wire. All right, now we know J. So we know that J is outside is 0 because it's a DC current, inside is only along the Z direction, I over pi R squared by definition of the flux. What about A? Well, for each point R in this region, which is from capital R to plus infinite, which eventually we are going to extend all the way to 0 in the filiform limit, we know that the vector A also has 3 components. It will have a component AX, which clearly has to be equal to 0, because JX is 0. AY, which also has to be equal to 0. And finally, we are left with AZ, which has to be, at any point capital P in space, has to be equal to the volume integral on the volume of the wire itself, on this region, which is the wire. The only component of J left is JZ, which we know is I over pi R squared, divided by any RQP in dV, the volume. Now, if you look at this one component, which is scalar, of the vector potential, does it remind you of something which potentially we've done in 242 for the electrostatic field? Well, we know that this is a scalar function, so it has to be exactly the same. It has to give as a result, the difference being the letters we use here, the same result as the electrostatic potential of a linear charge distribution with density lambda, where lambda is given by, so it's a linear charge distribution. Here we are considering still a volume, so we have an area, so it has to be pi R squared times rho. This is the typical trick. So pi R squared times rho gives me a lambda. So with this charge distribution, uniform charge distribution, we know that the electrostatic field associated with this charge distribution here, we found this in Phys 242, is equal to lambda over 2 pi epsilon naught R directed as UR. From the definition of electrostatic potential, we know that the electrostatic potential V associated with this, so if I confused sometimes V with phi, because sometimes the electrostatic potential is called phi, but let's try to keep it always consistent with capital V. So capital V is our electrostatic potential, so not to confuse, in that case we will call this dr cube. Here on, it's a little bit convenient not to get confused. So V has to be minus the gradient of E, so E is minus the gradient of V, so V clearly has to be minus, by definition, lambda over 2 pi epsilon naught natural logarithm of R. So this is our V. Okay? So we know from 242 that if I consider a quasi-filiform, that is a wire with a cross-sectional area pi R squared, with a density rho, which gives us a linear density lambda equal pi R squared rho, we know that E is given by lambda over 2 pi epsilon naught R UR. V from E equal minus gradient of V is minus lambda over 2 pi epsilon naught natural logarithm of R, because of course the derivative of this is 1 over R. So we know this result here. Okay? We already know this result from 242. I'm just reminding you, but it takes, you already know it, you already done it. Now, with this in mind, what kind of mapping do I need to perform in order to solve this problem with this knowledge? So I don't even want to bother. So here, if I encounter this problem, I need to start to think, okay, I need to perform this integral. And then I need to start to do it. Now, this could be simple. In this case, it's a simple integral. So it may take you a couple of minutes to do it, which is the same amount of time, probably less than what it's taking me to do this mapping, also because I'm trying to explain it to you. But this could have been a much more complicated problem where it takes like a month of calculations to do it later on in your career. So instead, if I do the following mapping, that is, I map V, if I map V to AZ, and I map ρ to, we have seen this in the previous video, to JZ divided by C squared, by means of this mapping, I can solve this problem straightforwardly. So let's use this mapping now. So if we do so, we know that V becomes AZ, and so the solution to AZ is going to be minus lambda, but lambda is pi capital R squared ρ, but ρ is JZ over C squared. So lambda is pi R squared ρ, JZ over C squared with the minus here, so lambda we have it, divided by 2 pi epsilon naught, this remains exactly the same, times the natural logarithm of R. Now, we already encountered this kind of constant here, C squared, in a previous video for Lorentz force. So C squared times epsilon naught is equal to actually mu naught in the numerator. So this we can rewrite it as minus, and of course, we know by definition that pi R squared JZ is actually I. So it's minus mu naught. So again, 1 over C squared epsilon naught is mu naught, CdV the Lorentz force. Pi R squared JZ is actually I, definition of steady current, minus mu naught I. So this minus we have it, pi R squared JZ we have it. This is mu naught divided by 2 pi, as expected, times the natural logarithm of R. This is my AZ. All right, great. So now we know AZ. Now we are doing the actually proper problem, which is we first calculate the vector potential, and from that we attempt to calculate the magnetostatic field B. So we know that B is the curl of A. So in a Cartesian coordinate system, the curl of A can be rewritten as, you've seen this before already, today, well, in a previous video. And so in this case, we are going to have a component X, which is going to be the partial with respect to Y of AZ minus the partial with respect to Z of AY. So AZ is what we have, so let's compute this one. So AY, of course, is 0, so this one does not contribute. AZ with respect to Y. So we know that R is, if I look at this construction here, can be rewritten as is the radius of a circle, and so is x squared plus y squared, Pythagorean theorem, under square root. So if we know that, we here have the natural logarithm of square root of x squared plus y squared. We are deriving with respect to y, with the plus sign. So we keep having a minus sign. The constants, which are mu naught I divided by 2 pi. The derivative of the natural logarithm, of course, is 1 over r. Now we need to derive this r, which is actually the square root of this quantity. So is this quantity power of 1/2. So is 1/2. This quantity power x squared plus y squared power of minus 1/2, which is actually 1 over r. And finally, the derivative with respect to y of x squared plus y squared is 2 times y. So 2 and 2 cancel out. And so this, as a result, gives us minus mu naught I divided by 2 pi, minus mu naught of 2 pi, y over r squared. Similarly, the second component, which is the y component, is going to be the partial with respect to z of ax minus the partial with respect to x of az. As always, x is equal to 0 ax, so it doesn't contribute. The derivative of az with respect to x with a minus sign becomes plus mu naught I over 2 pi. Now we are deriving with respect to x, so it's the same thing, but with an x instead of a y divided by r squared. And obviously the third component is 0. Why is that? Because it would be the derivative so this is bz. Bz would be the derivative with respect to x of ay, which is 0, and with respect to y of ax, which is 0. So the last one is 0. So we only have two components. If you remember a previous video where we've seen the vector potential associated with the uniform field B naught, we discussed about the parametric equations of a circle and its tangent points. So clearly, here we have that the x component of B goes as minus constant y, whereas the y component is plus constant x. So this is exactly means that the B field has to be tangent at each point of a circle with radius given by the norm of B. And so it has to be parallel, of course, to the xy plane, as expected. So in this cylindrical coordinate system, it has to be directed as var phi. So the direction is u var phi, okay? Because again, it's the parametric equations of such a tangent unit vector. And so finally, we can write B. From the Pythagorean theorem, the radius, again, is the norm of B. And so we need to square this quantity, sum them up, and the direction is u var phi. And so clearly this gives us mu naught I, as expected, divided by 2 pi. If you do this calculation, which is Pythagorean theorem, including x and y, it just gives you r here and u var phi. This is exactly what you get as a result. And so I let you do in Piazza the calculation that is in Piazza. I want you to calculate the norm, the radius of such a circle, the norm of B, using these equations up here. And of course, you will find this as a result. Okay, please do in Piazza. It's a very simple calculation. And it's directed as u var phi. Great. Also, note that now, if we were to perform finally the limit with the r that goes to 0 plus, as we intended to do, in this limit, effectively what we are doing is that we are taking this range and we are bringing it in the limit to a range which is from 0 to plus infinite. And of course, 0 is excluded because at 0 there is and 1 over r, so it diverges, so we exclude it. But that's the way we extend to the entire space. That is, we are effectively considering a filiform wire. Note that this capital R doesn't appear anywhere here anymore, and so this limit, of course, is trivial in this case. The only thing that does really is to extend the range all the way to the very line where the filiform wire, where a filiform wire would actually be, which is the z-axis. So to summarize this video, infinite wire we currently visited. We already calculated it, it's simple. However, I want to use same equation equal same solutions. And so we set it up with a quasi-filiform wire with a cross-section, which then we shrink down to a filiform wire at the end. We found J, which is just directed as Z, because by definition I is steady in the Z direction. Therefore, A can only have a Z component. Now from here, you could follow two different paths. One, you compute this integral, and you find this result. Or two, you note that this actually can be solved equivalently as if we were considering a line of charge with lambda equal pi r squared rho. Okay, we know the solution to that problem already. We know V for that problem. We do the mapping we have seen in the previous video, and so AZ, which is the equivalent of V by means of the mapping, has to be equal to this quantity here. We already know the result. And then we just find B as the curl of A, and this gives us the final result mu naught over I divided by 2 pi r u bar phi. So again, many students asked me in the past, why don't you calculate just the integral? Of course, again, you can do it. That's one path. The path I decided to follow is to say, okay, actually this, what if I consider a lambda with this density? Then I know the result, and I use the mapping of same equations as same solutions. And once again, the reason is that here it's simple, but later on in your career you may find a problem where it's actually important. And I find this all the time. It's actually something which I use a lot in my career. So it's very good to start with a simple case like this. That's it.